Welcome to Calculus. Today we will investigate evaluating limits of functions as x approaches a given number, focusing on direct algebraic substitution. We'll look at 7 total examples. Let's start by looking at 3 examples in this first segment. Let's head over to our notes screen. Here's our first example. It says evaluate the limit by direct substitution. So what we see in terms of our question is the limit, that's what LIM stands for, as x approaches 2 of simply 3. Now, when we're looking to evaluate a limit, what we do is we treat the 3 or whatever is there as an expression to the right of the limit as a function. So I'm going to start off by treating this 3 really as f of x equals 3. Now for each of these questions, a good way to start is by graphing that function so that we can see conceptually what are we looking for in terms of the limit. So I'm just going to sketch a coordinate plane. And for this type function, we just need to remember when y or f of x equals a constant, really what we're looking at is a perfectly horizontal line. So we'll graph this f of x equals 3. And I'm just going to sketch a horizontal line, so a line that's parallel to the x-axis going through the y value of 3. Now, once we have that sketch in place, I want to interpret the limit according to how it places on this graph of the function. We're interested in what happens to the y value as x approaches 2. So I'm going to find that place here on the graph, and then I'm going to trace up to the function at 3. And what we are looking for is what is the y value as x gets close to 2 from the left and from the right. And that two-sided approach is essential. In order to evaluate a limit, the value of y has to be the same as we approach the x from the left and from the right. Now we're in luck for this type of function, f of x equals 3. From the left, as x gets close to 2, we are approaching 3. As we are from the right, as x approaches 2 from the right, we're also approaching 3. So for this function, the way that we can evaluate is by writing the limit as x approaches 2 of the function 3 equals 3. Now keep in mind when we're asking about limit, we're really saying what's happening to the y value as x gets close to, in this case, 2. We'll box that as our final answer. So that's a very simple type function, just a perfectly horizontal line, a constant value. Let's look at another linear function, which is really a direct variation function 2x. So here we've got evaluate the limit by direct substitution of limit as x approaches pi of 2x. So just like we did with that first example, I'll start off by treating this 2x as a function. So f of x equals 2x. And again, we'll sketch the graph so that we can see conceptually what's happening as we are approaching pi from the left and from the right. Again, pi is an x value. So we'll graph this function. So recall to graph a direct variation, and we can think about it in terms of the slope-intercept for y equals mx plus b. The b value here is definitely 0. So it goes through the y-axis at 0. That's the origin. And let me make sure to write that, not y, but mx plus b. The second step when we're graphing a line like that is to plot a second point using the slope. So remember, our slope is the m value. So we'll say that m is 2. Really, we can say it's 2 over 1. So I'm going to rise 2 and run 1 to the right. We could continue that pattern, rise 2, 1 to the right, and sketch in that graph. So that graph is a linear function that it goes directly through the origin. Like we had done with the previous question, I want to locate that x value that we're looking for the limit. So I'm looking for pi. So I'm going to estimate. Pi is about 3.14. That's our traditional estimation of pi. Keep in mind it does go on forever without repeating. It's one of the famous irrational numbers in mathematics. So I'm going to locate pi. Pi is roughly here, 3.14. And then I'm going to trace up to the graph. So kind of at the upper part of that graph. And again, what we're saying is what y value am I approaching as x gets close to pi from the left and from the right. So conceptually, the graphs helps us visualize what the limit is asking. It's saying what's happening to the y values x is getting close to, in this case, pi from the left and from the right. Well, that gives us a conceptual idea of what's happening. Here, let's investigate our first real direct substitution. So as I'm doing direct substitution, one way to calculate a limit is just to plug in the value that x is approaching into the function. So I'm going to try to find f at pi. And unlike our first example, this actually has a variable. So I'm going to substitute pi wherever I see x. So I'm really looking at 2 pi. And I could leave it just like that. That would be the exact representation of the value of y as x is approaching pi. I could also multiply it out. In fact, I won't use the traditional equal sign. I'm going to use the wavy equal sign to say approximately 6.28. And we got that value by direct substitution into the function 2x. Now I can see it on the graph. If I were to check over here, we had gone up 4, 5, 6. Even from the graph, we can see if I traced over to the y-axis, definitely that approaches 6.28. So we'll box that as our answer. So pretty straightforward examples here to begin with. And a nice way to calculate that limit is just to try direct substitution. All right, let's take a look at a third example. So here we've got the next major group of functions from algebra. We've looked at a couple linear functions. The next main group are the quadratic functions. So like we had done, let's graph this one. So I'm going to create a plane. And I'm going to use a table to evaluate here the y values so that we can plot these points. So I'm going to put x there in the left column. And traditionally, we go -2 through +2 if we don't know much about the function. Really, that centers it, gives us a nice slice centered at the origin. So we're going to calculate those y values, which we can also call f of x, using these x values. So we'll start here, f at -2. So every time I see an x in that function, and again, I should probably write that the function is f of x equals that x squared minus 3x plus 5. So I'm going to start substituting. Now I do need to use parentheses because I'm squaring a negative number. So that'll make a difference for us. -3 times -2. So anywhere I see an x, I'm putting -2. And then I want to evaluate. So that becomes -2 times -2 is +4. Negative 3 times negative 2 is positive 6 plus 5. 4 plus 6 plus 5 is 15. So we got 1 point here, negative 2 comma 15. We'll keep going. F at negative 1. And again, this is to graph, but notice I am doing the direct substitution right here for the limit. So I do want to check out the graph, but I'm also kind of doing double duty here. I'm going to use this f at negative 1 for the evaluation of the limit. Minus 3 times negative 1 plus 5. Let's multiply that out. Negative 1 in parentheses squared is going to be positive 1. Negative 3 times negative 1 is plus 3 plus 5. 1 plus 3 plus 5 is 9. So in a way, we've already finished this problem, but I do want to see the graph again, because that helps us later as we go on and see more difficult questions about limits. What is a limit conceptually? Well, we'll keep going. So f at 0 is 0 squared minus 3 times 0 plus 5. So 0 squared 0, negative 3 times 0 is 0, plus 5 will give us 5. So we've got the point 0, 5, and that is our y-intercept for that parabola. Let's evaluate these last 2 points, f at 1. 1 squared minus 3 times 1 plus 5. 1 squared is 1, minus 3 times 1 is 3 plus 5. 1 minus 3 is negative 2. Negative 2 plus 5 is 3. That's the point 1, 3. And our last point here is f at 2, x value of 2. So that's 2 squared minus 3 times 2 plus 5. And that's 4. 2 squared is 4 minus 6 plus 5. And 4 minus 6 is negative 2. Negative 2 plus 5 is 3. So that is the point 2 comma 3. So definitely it looks like my vertex is in between these 2 points. Well, let's graph those. So negative 2, positive 15 is going to be hard to graph. I can try. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So all the way up here in the question itself, negative 2, 15. Let's catch negative 1, 9. 3, 4, 5, 6, 7, 8, 9. That's right here. 0, 5. Right on the y-axis. 1, 3. 2 is also at 3. So notice that that's that tipping point where the parabola goes down. I can predict that 3 would have the value of 5 just based on the symmetry. 4 should have the value of 9. So again, I'm going to take that framework and sketch the function. So we'll bring that down. Does look like the vertex is in between those 2 values, and back up. So there's our quadratic function, f of x equals x squared minus 3x plus 5. Now for the limit, what we're interested in is negative 1, x value of negative 1. So that's here on the graph. And just like we saw with those 2 previous linear examples, what we're interested in when we're saying the limit as x approaches negative 1, the question really is, what is the y value approaching as x gets close to negative 1 from the left? What's the y value getting close to as x approaches negative 1 from the right? Now with questions like these where you can just directly substitute, which we did here, you don't have to do a lot of algebraic manipulation. You're just plugging it in, getting the value. So we'll finalize this limit question. We'll say the limit as x approaches negative 1 And again, it's got to be the same from the left and from the right. Of the function x squared minus 3x plus 5 is, according to our work here in the table, 9. So again, just to repeat the idea, this 9 is a y value. And it's the y value that the function approaches as the x value gets close to this specific number that's under the limit. Okay, so those are our first 3 examples. Thank you for joining for the first 3. We'll return in just a moment for the remaining 4 limits by direct substitution. Thanks for joining. See you in just a moment.